Hello friends, welcome you all to the second lecture on function analysis and its applications. In this lecture, we will discuss on basic inequalities and their applications. Following are the contents of today's lecture: Young's inequality, Holder's inequality, Minkowski inequalities, and their applications. To prove some examples of metric space, we need to use the following inequalities: Young's inequalities, Holder's inequalities, Minkowski inequalities. First, Young's inequality. If alpha lies between 0 to 1 and two numbers a and b are positive, then a to the power alpha into b to the power 1 minus alpha less or equal to a alpha plus 1 minus alpha into b. Case 1, if a is equal to b, the proof is trivial. Why? If a is equal to b, then left hand side a to the power alpha into a to the power 1 minus alpha, that is a, and right hand side is a alpha plus 1 minus alpha into a. So this one is cancelled out, so equal to a. So this case is the equality case, that is the proof is trivial. Second case, if a is equal to 0, then left side 0 and right side this quantity first term 0 and we have this one 1 minus alpha positive, b also positive, that is right side positive. Hence, if a is equal to 0 or b is equal to 0, again the proof is trivial. Third case, if b and a greater than 0, then we define the function f(x) is equal to x to the power 1 minus alpha, which is a non-negative value for alpha lies between 0 to 1. We are given. So here f(x) satisfies the all conditions of Lagrange's mean value theorem for x lies between closed interval a and b. Therefore, we can find a point xi between a and b. So, by Lagrange's mean value theorem, f dash means differentiable of function f(x) at the point xi. Satisfies this condition, f of b minus f of a is equal to b minus a f dash xi. So, function is defined f(x) is equal to x to the power 1 minus alpha, then f of b is b to the power 1 minus alpha minus f of a to the power 1 minus alpha is equal to b minus a into 1 minus alpha xi to the power minus alpha, value of f dash xi. Differentiating f(x) with respect to x and putting x is equal to xi, we get 1 minus alpha xi to the power 1 minus alpha. Also, we know that 1 upon xi to the power alpha less than 1 upon a to the power alpha, because here xi is greater than a. Okay, so alpha is here lies between 0 to 1, then 1 upon xi alpha less than 1 upon a to the power alpha, that is xi to the power minus alpha less than a to the power minus alpha. So by this inequality we put this values of z to the power minus alpha, we get b to the power 1 minus alpha minus a to the power 1 minus alpha less or equal to b minus a 1 minus alpha a to the power minus alpha, because z to the power minus alpha less than a to the power minus alpha. Here equality case, because we discuss the whole case of the n inequality including this also. Or simplifying this, dividing by a to the power minus alpha, so we get a to the power alpha b to the power 1 minus alpha minus a less or equal to b minus a 1 minus alpha. Simplifying this, a to the power alpha b to the power 1 minus alpha minus a less or equal to, multiplying these two terms, so b minus a minus b alpha plus a alpha. So a to the power alpha b to the power 1 minus alpha minus a cancelled out. We have a alpha, this one, and b alpha, and here b. So b common, 1 minus alpha, that is a to the power alpha b to the power 1 minus alpha less or equal to a alpha plus b 1 minus alpha. This proves the Young's inequality. This noting point, if alpha equal to 1 upon p and q defined by 1 upon p plus 1 upon q is equal to 1 in equation 1. So we get a to the power 1 by p, b to the power 1 minus 1 by p less or equal to a by p plus b 1 minus 1 upon p. Okay. So by this. Therefore, a to the power 1 upon p, b to the power 1 minus 1 upon p less or equal to this 1 minus 1 upon p is equal to 1 by q, because 1 upon p plus 1 upon q is equal to 1. Therefore, 1 upon q is equal to 1 minus 1 upon p. So, putting the value of 1 minus 1 upon p as 1 upon q. So, we have a to the power 1 by p, b to the power 1 by q less or equal to a upon p plus b upon q. Second noting point, if a is equal to y to the power p and b is equal to z power q, then here a is equal to y to the power p, b is equal to z power q, that is y z less or equal to a y to the power p, that is y to the power p and b z power q, that is z power q upon q, that is yz less or equal to y to the power p upon p plus z to the power q upon q for all y z are positive. Holder's inequality, this is the important inequality. Here use of Young's inequality in Holder's inequality. So how to use? The statement of Holder's inequality, if p greater than 1 and q defined by 1 upon p plus 1 upon q is equal to 1, then summation I is equal to 1 to n mod of xi yi less or equal to summation I is equal to 1 to n mod of xi power p whole power 1 by p into summation I is equal to 1 to n mod yi power q whole power 1 by q for any real or complex numbers x1, x2 and so on xn and y1, y2 and so on yn. Proof. We know that p greater than 1 and 1 upon p plus 1 upon q is equal to 1 and x, y are positive, then from equation 3, this is equation 3, yz less or equal to y to the power p upon p plus z to the power q upon q. So we can write from equation 3 as x into y less or equal to x to the power p upon p plus y to the power q upon q. With equality case, if x to the power p is equal to y to the power q. Here if x is equal to 0 or y is equal to 0, then the inequality 4 is obvious. Now why x to the power p is equal to y to the power q is equality case. So we can see here left hand side x y. If x to the power p is equal to y to the power q, that is x is equal to y to the power q upon p. Okay. Then left hand side xy equal to x is y to the power q upon p into y, that is y to the power q by p plus 1 is equal to y to the power q plus p upon p. Also 1 upon p plus 1 upon q is equal to 1. Then p plus q upon pq is equal to 1. Therefore, p plus q is equal to pq. Then this is y to the power p q upon p. pq upon p, that is y to the power q. So left hand side x into y is y to the power q, and also from right hand side here x to the power p is equal to y to the power q. So y to the power q 1 upon p plus 1 upon q, 1 upon p plus 1 upon q is equal to 1. So y to the power q. Hence left hand side equal to right hand side, both values y to the power q. So here if x to the power p is equal to y to the power q, then the equality case holds. If x is equal to 0 or y is equal to 0, then the inequality here left hand side, if x 0 or y 0, then left hand side is 0, and right hand side 1 term 0 and we have one positive term. So inequality holds. Okay. Now we prove for x not equal to 0 and y not equal to 0. Then putting x is equal to mod of xi upon a and y is equal to mod yi upon b, where a is equal to summation I is equal to 1 to n mod xi power p whole power 1 by p, and b is equal to summation I is equal to 1 to n mod yi power q whole power 1 by q in equation 4. Okay, this is the equation 4. Then we have mod xi upon a into mod yi upon b less or equal to 1 upon p into mod xi upon a power p plus 1 upon q into mod yi upon b whole power q. Okay, taking summation of both sides from I is equal to 1 to n. Then a and b are constants, so we can write 1 upon ab summation I is equal to 1 to n mod xi yi less or equal to here 1 upon p, a as constant, so 1 upon a to the power p summation only on xi. Here I is equal to 1 to n. This summation from I is equal to 1 to n mod xi power p. Similarly, plus 1 upon q b to the power q summation I is equal to 1 to n mod yi power q. Clear? 1 upon p a to the power p, value of 1 upon mod xi power p from here. A is summation I is equal to 1 to n mod xi power p whole power 1 by p, that is a to the power p is equal to summation mod xi power p. So value of this can be written as a to the power p. Similarly, 1 upon q b to the power q into value of this one is b to the power q from here. Okay. So a to the power p into a to the power p cancelled out. Here 1 upon b to the power q into b to the power q, here cancelled out. So we have 1 upon p plus 1 upon q. 1 upon p plus 1 upon q is equal to 1. Okay. So left hand side 1 upon ab summation I is equal to 1 to n mod xi yi less or equal to 1. Then we have summation I is equal to 1 to n mod xi yi here less or equal to, this is the missing inequality sign, this one less or equal to ab. So putting the value of a is this one and value of b is this one here. So we get summation I is equal to 1 to n modulus of xi yi less or equal to summation I is equal to 1 to n mod of xi power p whole power 1 by p into summation I is equal to 1 to n mod yi power q whole power 1 by q. This is known as Holder's inequality for p greater than 1 and q defined 1 upon p plus 1 upon q is equal to 1. Holder's inequality for integral. So for discrete values, here Holder's inequality defined as this one: if function are non-negative real valued integrable function defined in closed interval ab, then Holder's inequality satisfies the following inequality: integral a to b f into g dx, here f and g is a function of x, less or equal to integral a to b pth power of fx dx whole power 1 by p into qth power of function gx integral over dx whole power 1 by q, where 1 upon p plus 1 upon q is equal to 1. In Holder's inequality, if we take p is equal to q is equal to 2, then we have summation I is equal to 1 to n mod xi yi less or equal to summation I is equal to 1 to n mod xi square whole power 1 by 2 into summation I is equal to 1 to n mod yi power 2 whole power 1 by 2 for special value of p and q as 2. Why? Because 1 upon p plus 1 upon q is equal to 1. If we put p is equal to 2, okay, then 1 upon q is equal to 1 minus 1 by 2, that is 1 upon 2, hence q is equal to 2. That is, if we take p is equal to 2, then we get q is equal to 2. So Cauchy-Schwarz inequality known as p is equal to q is equal to 2 in Holder's inequality. Cauchy-Schwarz inequality for integrals: if f and g are non-negative real valued functions, it is integrable function defined in closed interval ab, then for p is equal to q is equal to 2, we have integral a to b fx into gx dx less or equal to integral a to b square of fx dx whole power 1 by 2 into integral square of function gx from a to b whole power 1 by 2. That is the Cauchy-Schwarz inequality. Minkowski inequality. This is the important inequality also. If P greater or equal to 1, then summation I is equal to 1 to n mod xi plus yi power p whole power 1 by p less or equal to summation I is equal to 1 to n mod xi power p whole power 1 by p plus summation I is equal to 1 to n mod yi power p whole power 1 by p. Here p greater or equal to 1. In Holder's inequality, p greater than 1, and in Minkowski inequality, p greater or equal to 1. Here xi and yi are real or complex numbers, for each I is equal to 1 to n. To prove this, for p is equal to 1, the case is obvious, because here summation mod xi plus yi mod xi plus yi less or equal to mod xi plus mod yi. This is the well-known definition. If xi, yi as complex are real, then mod xi plus yi less or equal to mod xi plus mod yi. So for p is equal to 1, so this is the p is equal to 1, that is whole power 1 by p, that is 1, this is also 1, and this is the value of xi, yi. So taking in this case summation I is equal to 1 to n, this is summation whole, so that is summation mod xi plus summation mod yi. I is equal to 1 to n. So case is obvious for p is equal to 1. To prove for p greater than 1, we have mod xi plus yi power p. These terms can be written as mod xi plus yi power p minus 1 into mod xi plus yi. We can write this less or equal to this into as above mod xi plus yi less or equal to mod xi plus mod yi. That is total this less or equal to mod xi plus yi power p minus 1 into mod xi plus mod yi. Okay. Therefore, multiplying this term in these two terms. So we can write modulus of xi plus yi power p less or equal to modulus of xi plus yi power p minus 1 into mod xi plus mod xi plus yi power p minus 1 into mod yi. Okay. Therefore, taking the summation on both sides, so we get summation I is equal to 1 to n mod xi plus yi power p less or equal to summation I is equal to 1 to n mod xi plus yi power p minus 1 into mod xi summation on both terms. Okay. So similarly, summation I is equal to 1 to n mod xi plus yi power p minus 1 into mod yi. Okay. So by applying Holder's inequality, what is Holder's inequality? We have discussed just above as Holder's inequality. This one is modulus of x I into yi summation I is equal to 1 to n, then we have less or equal to this quantity. Here same as like this, here summation of two terms. Okay, so we can apply Holder's inequality and we get this one. Summation I is equal to 1 to n mod of xi plus yi power p minus 1 power q whole power 1 by q, and second term here mod xi, so summation I is equal to 1 to n mod xi power p whole power 1 by p, that is mod xi plus yi power p whole power 1 by q into summation I is equal to 1 to n mod xi power p whole power 1 by p. Here p minus 1 into q is p, because we know that 1 upon p plus 1 upon q is equal to 1. Okay, so 1 upon q is equal to 1 minus 1 upon p, that is p minus 1 upon p. Therefore, p minus 1 into q is equal to p. So, here p minus 1 into q can be written as p. Okay. Similarly, second term, this one, after applying Holder's inequality, we get this summation mod xi plus yi power p minus 1 into mod yi less or equal to summation I is equal to 1 to n mod xi plus yi power p whole power 1 by q into summation I is equal to 1 to n mod yi power p whole power 1 by p. So, using equation 5, 6 and 7, here 5, 6, this is 7, putting the values of these and these in equation 5. So, we get this one. Summation I is equal to 1 to n mod xi plus yi power p less or equal to summation I is equal to 1 to n mod xi plus I power p whole power 1 by q common, and summation I is equal to 1 to n mod xi power p whole power 1 by p plus summation I is equal to 1 to n mod yi power p whole power 1 by p. Okay, so left hand side this one and right side this. So terms is same here, this and this, but whole power here 1 and here whole power 1 by q. So dividing by summation I is equal to 1 to n mod xi plus yi power p whole power 1 by q both sides. So we have summation I is equal to 1 to n mod xi plus yi power p whole power 1 minus 1 upon q less or equal to summation I is equal to 1 to n mod xi power p whole power 1 by p plus summation I is equal to 1 to n mod yi power p whole power 1 by p. Again, putting the value of 1 minus 1 upon q is equal to 1 upon p, because 1 upon p plus 1 upon q is equal to 1. 1 upon p plus 1 upon q is equal to 1. Then 1 upon p is equal to 1 minus 1 upon p. So putting the value of 1 minus 1 upon p, sorry, this is q. Putting the value of 1 minus 1 upon q is equal to 1 upon p here. So this proves the Minkowski inequality. Minkowski inequality for integrals. Similar proof here. So we can avoid the proof for integrals. So similar results can be written as follows. If f, g are non-negative real valued function defined on closed interval a, b, then integral a to b f of x plus gx whole power p dx and total power 1 by p less or equal to integral a to b ps power of fx dx whole power 1 by p plus integral from a to b of the function gx power p dx for p greater or equal to 1. This is the Minkowski inequality for integrals. For examples, what is the application of the above inequalities? So, here to prove the some metric spaces, that is fourth condition of metric, we use the application of Minkowski inequality to prove the fourth condition of some example of metrics. For example, Euclidean space Rn. To prove the Minkowski inequality, we need Holder's inequality, and to prove Holder's inequality, we need the Young's inequality. So, above inequalities are very important inequalities. So, how to apply Minkowski inequality in this example? Suppose Euclidean space Rn. The Rn is a set of all ordered n tuples where each element of the tuples is real numbers written as Rn is x1, x2 and so on xn, where x1, x2 individual in R. x1, x2 are individual in R, that is n terms, that is Rn. If x equal to x1, x2 and so on xn in Rn and y equal to y1, y2 and so on yn in Rn, then Euclidean metric defined dxy equal to under root x1 minus y1 square plus x2 minus y2 square plus and so on xn minus yn square. This expression can be written as in short way dxy is equal to summation I is equal to 1 to n xi minus yi square whole power 1 by 2. Then D is metric and ordered pair R and D is a metric space. To prove the metric, we have four conditions. So, first dxy greater or equal to 0. Since dxy defined as summation I is equal to 1 to n xi minus yi square whole power 1 by 2. Then square of xi minus yi always greater or equal to 0. Then dxy greater or equal to 0. Okay. xi, that is the fixed term, I is equal to 1 to n. So, sum of all I is equal to 1 to n, each term also positive, because here each term is the square of the x1 minus y1 plus x2 minus y2 and so on xn minus yn. All terms are square terms, that is always greater or equal to 0. So, each term of this expression are positive. So, dxy greater or equal to 0. The metric D always greater or equal to 0. Second condition, dxy is equal to 0 if and only if x is equal to y. If dxy is equal to 0, then dxy defined by summation of I is equal to 1 to n xi minus yi square whole power 1 by 2 is equal to 0. It means each term is square term. So, always positive. Each term always positive. So, here dxy is equal to 0. It means we have only one condition if each term is 0. That is xi minus yi is equal to 0 for all I is equal to 1 to n. Okay. So for each I which leads xi is equal to yi for all I. Therefore, we conclude that x is equal to y. Okay. Conversely, if x is equal to y, it means xi is equal to yi. For all I, then dxy is equal to 0. Okay. So if x is equal to y, it means x1, x2 and so on, xn equal to y1, y2, y3 and so on, yn. Okay, so x1 is equal to y1, x2 is equal to y2. That is xi is equal to yi for all I is equal to 1, 2 and so on n. So dxy is equal to 0 if and only if x is equal to y. Third condition, dxy is equal to dyx for all xy belonging to Rn. By the definition of dxy define this one. So this is the square term. So we can adjust as yi minus xi square. Okay, there is no change. So as per definition of dxy, this expression can be written as dyx. Therefore, dxy is equal to dyx. Clear? Okay. Fourth condition. This is the important condition. dxy less or equal to dxz plus dzy. So, how to say this inequality holds? Since dxy is defined summation I is equal to 1 to n xi minus yi square whole power 1 by 2. So, this expression can be written as this. Here we add zi and subtract zi. Okay, there is no change. So, this expression can be written as this xi minus zi plus zi minus yi. Okay. So, this is the two terms xi minus zi plus zi minus yi. We know that the Minkowski inequality summation I is equal to 1 to n ai plus bi power p whole power 1 by p less or equal to summation I is equal to 1 to n mod ai power p whole power 1 by p plus summation I is equal to 1 to n bi power p whole power 1 by p. That is by Minkowski inequality, Minkowski inequality summation mod ai plus bi power p whole power 1 by p less or equal to summation mod ai power p whole power 1 by p plus summation mod bi power p whole power 1 by p. Okay, so here two terms ai and this is bi type and p is 2 greater or equal to 1. So we can apply the Minkowski inequality. So less or equal dxy less or equal to summation I is equal to 1 to n summation mod xi minus zi square whole power 1 by 2 plus summation I is equal to 1 to n zi minus yi square whole power 1 by 2. So as per definition of dxy, this can be written as here xi minus zi. So this expression can be written as dxz plus this one dzy. Okay, hence fourth condition also satisfied. So we can say that R&D is a metric space. It is also known as Euclidean metric space. Similarly, second examples of Euclidean space Rn. Let X is equal to Rn and denote the set of all ordered n tuples of real numbers of a fixed value n belonging to n. Let X is equal to x1, x2 and so on xn is the element of Rn. Also, y is equal to y1, y2 and so on yn elements of Rn. Define the mapping D such that Rn cross Rn to R. Then dxy is equal to max of x1 minus y1, x2 minus y2 and so on xn minus yn. Then D is metric for. So this is a very simple example. We can prove here as above examples. Here this is the modulus value. So greater or equal to 0, that is dxy greater or equal to 0. If we change x place of x1, y1 and here y2 minus x2 and this one yn minus xn, that is no change. So we can write this is dxy is equal to dyx and each terms is modulus value. So that is positive. So dxy is equal to 0 if and only if x is equal to y. Also we can prove. And if we add z1 and subtract z1 and in this term add z2 and subtract minus z2 and so on. So we apply property mod z1 plus z2 less or equal to mod z1 plus mod z2. So we can prove dxy less or equal to dxz plus dzy easily. Third example, the LP space. The LP be the set of all sequences x is equal to xn, n is equal to 1 to infinity such that summation n is equal to 1 to infinity mod xn power p less than infinity and define the metric this for p greater or equal to 1. Then LPD is metric space. Already we have discussed the same examples here. Summation I is equal to 1 to n mod xi minus yi power p whole power 1 by p. Here we extend the terms from 1 to infinity with condition this one less than infinity. Okay. So we can prove easily as per that example. Following examples also can be proved easily as above. The spaces C and C0, where let C denote the set of all convergent sequences and C0 is the set of all null sequences, that is the set of all sequences which converge to 0. Then both C and C0 are metric spaces under D defined by dxy is equal to supremum of xn minus yn for all n belonging to n, where x is equal to xn and y is equal to yn are any two elements of C and C0. Next example, the space C01, let C01 denote the collection of all real valued bounded continuous functions defined on closed interval 0 to 1. We define dfg supremum of mod fx minus gx such that x belonging to 0 to 1 as a metric for C0, 1. So these examples can be proved easily. Okay. So conclusions. In this lecture, we have discussed the basic inequalities and their applications. Also, we have given some more examples of metric spaces. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Narisi. Second, function analysis, John Valley, written by Erwin Krejcik. Third, function analysis by Vivi Lemieux. Fourth, function analysis written by Waterudin. Thank you for the attention.